my dyslexic ass. I wrote like in my givens when I was writing like, oh, here are the numbers that they gave me. I wrote 6.0, and then when I was doing the calculations, I wrote 9. And I didn't even look over my work. I was like, that's my answer. I got it right. Got it wrong, and I was like, what the fuck did I do wrong? Look at it.
What did you get homework?
No, I think that this one I put unacceptable mistake. Wrong.
Hawk's cake.
Oh yes.
Yes, bro, I love it.
Yes, my best friend's dad. He's like lives in an air conditioning company, and they do the AC for them. And
For
like,
real?
yeah, they give them like a week.
Next time we're gonna have our first midterm. It's gonna cover chapter 12 and chapter 13. Chapter 14, which I'm gonna start today, is not covered in the exam. So lecture of today is not included in the exam. The only thing that are included in the exam is the kinematics, the first chapter, like the position, the velocity, the acceleration, and the relation between them. And chapter 13, which includes the kinetics, the Newtonian problems, like and all the problems, like in Cartesian, the polar, and the tangent, and normal. Try to familiarize yourself with the problems. The exam is gonna be 60 minutes. It's gonna start at 11, okay, and it's gonna end at 12. Maybe I give extra time, it depends. It's gonna be 4 questions. Some questions is gonna be very, very small. I'm gonna ask you just to draw something, like not solving an entire problem or solving a piece of problem. And problems is gonna be long, like you have to start step by step. So try to be focused, use your time, allocate your time perfectly so that you don't miss big portion of the points. Try to get as much points as you can, okay? If you don't understand or if you don't get, like, because some students when they get problems and they don't know what to do or where to start to draw something, start to think your thought process, put them on the paper, you get points. Free body diagrams, kinetic diagrams for problems, if you didn't draw them, you will not get points. You will lose some points per problem. You need to draw. We are engineers. We draw everything. That's how I used to in my bachelor. Any problem that I get, I try to draw it. Even problems that is already drawn in the exam sheet, I put them, my answer, and start to think with the forces, with the acceleration. Try to think, so draw as much as you can. All right, so yeah, that's good. So because I don't have to print 65 or 64 equation sheet, try to print your equation sheet and print it with you. Okay? I'll try to print some, so if somebody like forget to print or bring his equation sheet, I will give him one, but I'm not gonna have like 65 equation sheets. I believe that every one of you has the equation sheet printed, and actually I uploaded a high resolution one, like a PDF one, not scanned one. So try to check Canvas. I just uploaded last week to maybe print the high resolution one. This is the only thing allowed in the exam. You're not allowed to have your notes, your references, or anything. The equation sheet is the only thing is allowed. Right? Does anybody have any other questions? Yeah, it's gonna be here in this room. All right. So today we are going to talk about chapter 14. You guys studied dynamics before somehow in high school or something, right? You didn't study dynamics at all? And even in math? Like in the math you don't get taught dynamics? Also in math, did you guys study the differential equations? Differential equations, right? Like you can solve differential equation. Did you guys study partial differentiation? So all these stuff. All right. So today we are going to talk about chapter 14, which is about work and energy. Okay. So work.
I don't remember.
Work is the amount of energy transferred to a particle to change its position. Like if I have, for example, a body here, and you want to move this body from this location number 1 to this location number 2, you need to apply a force on this body somehow, for example, this way, or whatever way that you're gonna have, maybe this way, so that you can transfer this body from this position to this position. So this is called the amount of energy transferred to a body to change its position. So a force F will do a work on a particle only if the particle undergoes displacement in the same direction of the force. For example, this is a body. This is a body. If you put a force this way, and this body is moving on the other direction, like it's moving this way, so the only force that moved the body this way is the component of the force in the direction of the displacement. Like let's assume theoretically, if you apply a force on a body this way and the body moved on the other way, so this force didn't do any work on this body. Okay, it needs to be in the same direction. Like for example, if I have a body here, okay, and I put a force F this way, and this body moved this way, so the component of this force in this direction is the only component that made work. Okay, so how we can describe this mathematically? So let me. So if I have a general back like this, and let's say that I have my body moved from S1 and got to S2, and let's say here's the radius. So if I want to describe the location of this body, so this is position number 1, and this is position number 2, and let's put a force, for example, here, F, force, and this body at some point at the general location came here, so this force is like this, F vector. And this body is moving on this curve, something like this. So to describe, let's say that for example that the position is keep changing because the location is keep, like we need to describe it. So we take like for example an infinitesimal distance here, like this distance, and we call it ds, or the position vector dr if you describe it as a position. So the infinitesimal work du is going to be equal to the force vector dot product multiplied by the dr position, the change in the position. And you guys know the dot product and the cross product, okay? So this is a dot product, the force vector multiplied by the change in the position. And if we want to get this dot product, you guys know how we do a dot product? So it's going to be the absolute of this vector multiplied by the absolute of the change in the position vector multiplied by cosine theta. Excellent. The dot product, if you have a vector x and another vector y, and if you want the dot product of x vector multiplied by the y vector, so it is equal to the magnitude of x vector multiplied by the magnitude of the y vector multiplied by cosine theta, the angle between the two vectors. This is the same thing, like if this is dr, so I put f dr cosine theta. Right, so this is gonna be here. So if I want to move from just du, I want to get the entire work is done on my particle, U from position 1 to position 2, so here's position 1 and here's position 2, I need to integrate this relationship. So I integrate this relationship, the F vector dr vector, from position 1 to position 2. It is the same thing if I said that this is gonna be from S1 to S2, like from this one to this position, I'm gonna get the whole distance, I subtract them, and then this is gonna be the absolute value of the force. This is not a vector, this is the magnitude, multiplied by ds multiplied by cosine theta, the angle between the force and the distance. And this is actually makes sense. How? Like let's say this is the S, okay? So this is the, let's say that this is ds. And I have a force going this way. And this is the angle between ds and the force, theta. So the only force that makes work is the force that is in the direction of ds. So I need to find the component of the magnitude of F in the direction of S. And actually I need to find the two components. So I found out that this component of the force in this way, it's F cosine theta. So the work done is equal to F cosine theta, the component of the force in the direction of the displacement, multiplied by the displacement. And this is a general rule. If you have a force acting on a body, and then this force moved this body here from this position, and this is distance S, so it's gonna be F cosine theta multiplied by S, and actually the theta between F and S is 0 because both of them are in the same direction. So cosine 0 is 1, so this is gonna be F multiplied by S because all the force is in the same direction of the displacement. So F multiplied by displacement is gonna give you work. So if you have a force horizontal, pushing a body horizontal, and move this body, let's say a force 10 Newton, and push the body horizontally and move this body 2 meters, so you multiply the 10 Newton by 2 meters, you get the work. So the work is force by displacement. Okay, you multiply the force by the displacement, but the force needs to be in the same direction of the displacement. If I give to you in the problem the force in the same direction of the displacement, you don't have to do cosine theta. So you take the whole force, multiply by the whole displacement, you get the work. But if this force, for somehow I put it this way, so the body's moving this way and the force is going up, so all the components that goes up doesn't do any work. So you need to find the two components, F cosine theta and F sine theta. F cosine theta multiplied by S is equal to the work, but the force, the component of the force that goes up doesn't do any work. Okay? Yeah.
So if let's say the case was the ball would go up instead of the right, would you use F sine theta? Because
No,
that's
it's
not-
always F cosine theta. If the body goes up, so theta is equal 90 degrees, so F cosine 90 degrees is 0, so the work is equal to 0. The work of this force. Okay? Like for example, I have my body here, and I pushed with a force this way. And somehow this body moved down. Okay? So this doesn't do any work on this body because the body went up. There is no displacement in the direction of the force to multiply with. Okay? But like let's make this example, like let's say this body's here and this is the ground. And there is a force on this body this way, wind force. Okay? And this body is still moving down, didn't make any shift to the left. All the displacement is going down. So this force didn't do any work on my body because my body didn't move any x direction. All the movement is in the y direction. And let's say this body has a weight W and make a distance S. So the work U is equal to W of the body multiplied by the S, and it's a negative because it's going down. So this is the total work on my body. It's going down. So all the wind force didn't do any work. All right, so does anybody have any other question?
Okay, so if it went down, but it also like if it went like this, you do
So
the-
this one did work.
Yeah, so if that one did work, we would do the weight
F-
times the distance this way, and then the force of wind times the distance on the x, right?
Yeah, like
We
you
have
are
to-
saying that this body came here
Yeah.
from here, and there's a force F this way.
Yeah.
So this is the direction of the F, this is the direction of the displacement. You need to find the cosine theta between them, and then you will get the component F cosine theta and multiply it by ds.
Okay.
So still not the entire force, because this body didn't move horizontally, okay?
Would we add the two words at the end, or do we?
Yeah, all the
separate it?
forces is gonna do work. The weight of the body, we're gonna talk about all the forces that can make work on rigid bodies.
What?
Parts. Yeah.
Also, there's the force that said instead of going in the x direction, it's almost like in the same way that it went down, like, let's say like this.
Like
it's-
this, right?
It applies, yes, in the same, in the
Like
same
if my
direction.
force is this way,
Yes, yes.
so the whole force is gonna be multiplied by this. But actually, I don't wanna confuse you. I always want you to use F cosine theta. And if the force is in the same direction of the displacement, theta is gonna be 0, and cosine theta is gonna be 1. So it's gonna be F multiplied by S. But
Doesn't matter.
yeah, but if you are expert enough and identify that, yeah, this whole force is in the same direction of the displacement, so I don't have to do the cosine theta thing and multiply them directly, you can do that. Alright, so well, same thing if we want to find work, as we said. So this is the relationship of this chapter. This is very, very important one. The work from 1 to 2 is equal to the integration from position 1 to position 2, f cosine theta multiplied by ds. Okay? So if f is constant, you can get it out of the integration and then integrate ds. Sometimes maybe I give you f as a function of s. So you have to put them in the integration and integrate that. So you don't take f out of the integration unless it's constant. Unless I tell you this force is 400 pounds, or the weight of the body is still a force, is like 10 kilograms. So as soon as f is constant, you can take it out from the integration sign and start the integration. This is very, very important rule. Do you guys remember when we said the integration, we can get it graphically? Do you remember how? The integration is something that you integrate over a boundary, like let's say from S1 to S2. If you have the relationship between f cosine theta and s on the x-axis, let's say it somehow became a relationship like this, and if you are looking at the distance or at the location from S1 to S2, if you find out the area under this curve within the boundary from S1 to S2, this is gonna give you the value of this integration, okay? So this is how we can represent integration graphically. All right, so let's find out the work of the different forces that can act on a body. And we are gonna start with the work of the body weight. Number 1, work of weight. Okay, so the work of weight is something like this. The work from point 1 to point 2. Let's put an example. I have, this is x and this is y. And for example, I have this is the path that my body's moving in, okay? And let's say my body started from here and moved down here. At any general location, my body was here. And I'm only looking at the work done by the body weight. The body weight is always going down, okay? So the body moved from, let's say this is y1, and went to y2. And this distance is delta y, the distance from here to here. Alright, so the work done by the weight u from 1 to 2, since it's going down, so it's a negative, so it's a negative the force w multiplied by delta y. This is how you can get the work done by the body weight, and that's actually makes sense. Why? You have, for example, your body's here and move down here, and the force is going down. So you are only interested in the force in the direction of the displacement, right? Or the displacement in the direction of the force. So you either need to find out the weight, keep getting the components of the weight in the direction of the displacement, and then multiply by the entire displacement, but it's much easier to find the displacement in the direction of the force. So my force was here going down and was here going down, and this is the displacement that my force done. So it's W multiplied by delta Y. So this is actually the force. If we want to prove it, we can prove it. Like, let's start. Let's find the W. W is a vector, the weight vector, and has a magnitude of negative W, the weight of the body, and in the direction of j hat. It's a negative j hat, so I have the negative here, and this is j hat, which represents the unit vector of the y direction. Okay, and the second thing is the dr vector. How the position is it changing? Dr vector. So the dr vector is something like, for example, like if I'm saying I'm gonna take a small piece here, this is a change of the position for a very, very tiny, and it's a dr vector, so I'm gonna take it as dx component, like I'm gonna divide this into dx and a piece dy. This is the dr component. Dx in the I hat direction plus dy in the j hat direction. So this is how this small tiny piece look like. And the second thing is I want to get the work u from 1 to 2. So definitely it's the integration from r1 to r2. So from this position r1 to this position r2. F vector dot product dr vector. So it's the same thing, it's gonna be from R1 to R2. I'm gonna put this negative W in the j hat direction, multiply dot product by dx in the I hat plus dy in the j hat direction. Okay, so I put this vector and this vector. Let's multiply dot product. If you wanna do a dot product, you need to multiply this by this and this by this. Okay, for the dot product thing, this is the I hat and this is the j hat. So that the dot product can have a value, both vectors should have the same direction. How? Like, as we said, like the dot product, like let's say x vector dot product y vector is gonna be equal to x multiplied by y, multiplied by cosine theta. So if the two vectors has, one of them has I, one of them has j, so the theta between them is 90 degrees. And the cosine is gonna be 0. So for the dot product to have a value, they both should have the same direction. If they don't have the same direction, one is I and one is j, so the angle between them is a 90 degree. So let's do it here. Let's multiply this. This is a component in the j hat and one in the I hat. So you multiply something is going in the I hat direction, but something is going in the j hat direction. So the angle between them is 90 degrees. So it's gonna be this, the value of this, multiplied by the value of this, multiplied by the theta between them. So this is gonna be negative W. This is the magnitude, and the magnitude of this is dx, multiplied by the cosine theta between the j hat and the I hat, which is 90 degrees. This is gonna give you 0. Let's go to the second component, plus this multiplied by this. So it's gonna be negative W multiplied by dy multiplied by the cosine theta between them, which is 0, because j hat and j hat, I'm asking you, the component going in the j hat and another component is going in the j hat, the angle between them is 0, so this is going to be equal to 1, and this is going to be end up with negative w dy multiplied by 1, but don't forget the integration sign. Once we remove the r and we put x and y, and right now I'm ending up with only y, so I need to integrate from y1 to y2. So this was gonna give me that the work from work from 1 to 2 is gonna be equal to the integration from y1 to y2 negative w dy, so it's gonna be negative w y2 minus y1, so negative w delta y. Okay, and that's actually what is given here. So it's always the weight of the body multiplied by the displacement that this weight made. Okay. Alright, and always the weight is going down because it's in the gravity direction, so you look how much distance that this body cut in the y direction. Let's come to the next force, number 2. The next force is the work of a spring. The work of a spring force. So you have a spring, something like this. And there is a force F on the spring is going this way. So this is F. So the spring is gonna have an internal force that is always in the opposite direction of the applied force is equal to Fs, which is the K of the spring multiplied by the delta inside this spring. Or we can call it S, the displacement, and it's always negative. So let's say after you apply this force, this is spring, get to the position here. So this is the initial position, and this is the final position. So let's say this is S1, this is S2, and this is delta S. So the force of the spring from 1 to 2, from this position number 1 to this position number 2, so it's gonna be the integration from S1 to S2, the F spring multiplied by the ds. As soon as both forces are in the same way, I can say that cosine theta is equal to cosine 0, so it's gonna be 1. So, but let me remove Fs and put negative S1 to S2. So I'm gonna let's write this clear. Fs is negative K multiplied by S. K multiplied by S ds. Let's integrate this. I'm gonna take negative K outside, and when I integrate S ds is gonna be, you guys know? What is the value of this integration?
It's
S squared over 2. So this is gonna be negative K S squared over 2, and I need to substitute with the boundary of the integration S1, S2. So this is gonna be negative 1 over 2 K multiplied by S2 squared, S1 squared. So this is how we can get the work done by a spring. You need to find the initial position, the final position. Like if I told you in an example, a spring was stretched by 1 meter. Like I have a spring, and it started at the position when it was stretched 1 meter, and you put more stretch of 2 meters. So what is the initial position and what is the final position? The initial is 1, the final is 2. No, the final is 3, because we added more 2, okay? So it's gonna be 3 squared minus 1 squared. Don't put 2 squared, okay? All right, so this is the work done by a spring. The force number 3 that we are gonna study is the constant force. And that's actually what we put here. This one, FDS cosine theta. But let me write it here. Number 3, work of a constant force. The work of the constant force, look at this rule. U12 is equal to the integration from S1 to S2 F cosine theta ds. So you can take F cosine theta out and you integrate from S1 to S2 ds. So this is gonna give you F cosine theta S2 minus S1. This is any general force. And this is actually this rule, F ds cosine theta. If F is constant and cosine theta is constant, take them out, integrate ds, put S2 minus S1, and then you finalize getting the work. So let's solve a problem. Okay. This is example 14.1. So the example is something like this. You have an inclined surface with an angle 30 degrees. And there is like a wall or something, and there's a spring that is already stretched. And then you have your body here, and this is position number 1, and your body at position number 2 is here, S2. The original position is already stretched by 1 meter. No, by 0.5 meter. So S1 is equal to 0.5 from here to here. This is already stretched. This is the unstretched position of the spring. The unstretched position of the spring, that means that the work in the spring is 0. But once you pull your body this way 0.5 meters, so the spring is exerting work. So this is equal to 0.5 meter, this distance. This is where my body started, and keep moving until it gets to the final position. And this S from here to here is equal to 2 meters. The distance from this position to this position. The body has a mass, so S final. So what is the S final? S2. I have S 1.5. S2. The unstretched position, the 0 is here. My body started at 0.5 from the unstretched position, so S1 is 0.5, and then I put extra 2 meter until it gets to S2. It's gonna be 2.5. This is the final position, because we always measure from the unstretched location of the spring, because this is where we have the 0 work. Okay? All right. The body has a mass of 10 kilograms. This is all the information given in the problem. The body mass, the unstretched, the initial position, the final position, and also I'm giving you the K of the spring, which is 30 Newton meter. So what I'm asking for is the total the total work done by all the forces until the body came here. I want to find the work total. So let's find out how many forces that are exerting work in this problem. There are many, many forces that can exert force. Some of them are equal to 0, but some of them has a value. So let me take this body here and we can try to find out the forces on this body. Once you find the forces on this body, you will be able to find out what are the, this is my body, okay? What are the forces on this body? The weight, so the weight is gonna have a force, because why? Because this body moved it from here to here, so the weight, so you need to overcome the weight to come here, so the work, the weight have done force. Okay, so I have a weight, what else? The spring is the force going this way, F spring. What else? Friction. So if this body is not smooth, so, and I didn't tell you anything about this surface, so we are gonna neglect the friction. But if it's not, and if this body is moving up, so the friction is going down. What else? What other forces? I'm talking about forces, not work. Normal force, right? But does the normal force is gonna exert work? Why? Because it's in the opposite direction of the motion. So the body is moving this way and it's perpendicular. If the force is always perpendicular to the motion, so this force is gonna never make any work in our problem. So normal force doesn't do any work because my body is moving this way and the force is going this way. So the angle between the motion direction and the force is 90 degrees, so cosine 90 is gonna be 0, so this force is not gonna do any work. However, Fs is always making negative work, because you are pushing your body this way, the friction going the other way, so it's always negative, okay? So I have many forces that can do work, so let's take them one by one. Number one, let's find out the weight, the work done by the weight, so weight. So as we said, the weight is gonna be equal to the work done by the weight is gonna be equal to W delta Y. So you have either two options. You need to find the
I
yeah.
have a question before. Where is the force that is pushing this object up?
The force, okay. Oh yeah, sorry, we forget to put this force. You are also given, that's the term, yeah. So you have a point here and you have a force here, B. This is an external force. Is equal to 400 Newton. This is also given in the problem. So this is an external force, so you have to put it here. B 400 Newton. So I have 5 forces now. Okay? Alright, so let's get to them one by one. So the work done by a weight, so it's easier. I know that the weight is going down, right? Something like this. So you have to do two things, one of two things. Either to find the component that is in the direction of the motion, or find the displacement is in the direction of the force. I know that my weight is going down and the distance, so I have the inclined distance. So you need to find, for example, let's find this angle. This angle is 30 degrees and make this. Okay, so this and this is, okay, so this angle is going to be 30 degrees as well. So you will have W cosine 30 and W sine 30. So you need to find W. This right now is not the cosine. So what I'm doing right now, I'm trying to find the component of W in the direction of the displacement. You are going to say, okay, I need to find W cosine theta or F cosine theta multiplied by the displacement, but you have to do it this way. You have to, for example, like my body made a movement like this, and my weight is gonna be something like this. So this is W, and this is the distance, S. So this is the angle between them. It's gonna be very, very different. Or you can make it something like this, and remove this, and find this angle. If you try to find this angle, this is W. So this is gonna be the angle here. If this is 30 degree, this is 30, so this is gonna be 60. Okay? So the angle between W here and the S is gonna be 60 degrees. So you are gonna say W multiplied by S multiplied by cosine 60. This is the angle between them. But what I did here, I did it in a different way. I tried to find the component W cosine theta and W sine theta. So this is W cosine and this is W sine. Sine what theta? The 30 degree. So W sine theta is in the same direction of the S, but it's a negative way. So it's gonna be W sine 30 multiplied by S2 or cosine 60, and both of them has the same value. Okay? So either two ways are right. If you want to find out the entire W and the entire S and find the theta between them, do it. So it's gonna be W S cosine 60. If you want to analyze the components, find the force in the perpendicular direction and the force in the direction of the motion, so you are gonna end up with W sine 30. So what I'm looking for, what is the component of the force in the direction of the motion? The perpendicular component is not in the direction of the motion, so this doesn't gonna put any work. This one is gonna make work. So let's go this way. Let's say this is gonna be equal to the integration of the force cosine theta ds from S1 to S2. So F right now is W, the W is negative, so you can say negative W. The angle between the two forces, we find it out as a 60 degree, so you can say W cosine 60, and you will integrate ds from S1 to S2. So this is going to be negative W cosine 60 multiplied by S2 is 2.5 minus 0.5, and W is gonna be, we can remove actually W and put 10 kilogram multiplied by negative 10 multiplied by 9.81. So once you calculate this, it's gonna give you negative 98.1 Newton meter. So you either put Newton meter or Joule, so both of them are the same thing. You guys got it? And actually there's another way that we can do this. I know that the weight is going down. I try to find the vertical distance between here and here. I try to find delta y, like I can find y2 and y1. I know that this is a triangle. Perpendicular is something like this. I know this angle is 30. This is 2. So this is gonna be 2 sine 30, and this is gonna be 2 cosine 30. So I know that delta y here is 2 sine 30. So if I multiply W by 2 sine 30, which is gonna be, here is 2.5 minus 0.5 is gonna be 2. We have cosine 60 is the same value of sine 30, and W is 10.981 is gonna be the same thing, okay? So there's different ways to do it, just like you need to understand the concept. It is the distance in the direction of the force. I know this is the distance in the direction of the force, so this is 2 sine 30, multiply them by W. Or if you wanna go to the basics, so it's F cosine theta multiplied by ds. Try to find F, try to find ds, and try to find the theta between them, but do it right. Do it the same way that I did it here. So this is the theta between them. Does anybody have any question?
I got what you said, I just wanted to ask, in this case, we were able to take out W outside because W in this case is a constant
Yeah.
force, right? Is there cases where it's not, like,
Sometimes,
yeah,
it
like
can
it could be variable?
like a motor that is changing the force, so it can be, but I have to give you a variable that you can integrate. Like it can be a function of ds. If it's not a function of ds, how you can evaluate? If it's function in time, it's gonna be much more difficult, so you have to tweak your integration. But I'm not gonna do that. Most of the problems, the forces is gonna be constant. Does anybody have any questions? All right, so there's different ways that I can find the work done by the weight of the body. So you either find the angle between them and multiply the magnitude of the force by the magnitude of the distance, by the cosine angle between them, or you multiply the magnitude of W by the distance in the direction of the weight W. So okay, we got the work done by the weight. So let's, number 2, get the work done by the horizontal force. Work done by B. So what do you think? B is horizontal. I'm not sure if you still guys can see the B. So B is horizontal, is going this way. Here's my body, and here's the final position, and B is equal to 400. So I need to find out the component of the B in this direction and the component of B in this direction. So the component of B in this direction, so this angle is 30 degrees, so this angle is 50 degrees. So definitely this is B cosine theta, and this is B sine theta. So the force, my body moved this way, and this is the force perpendicular to the movement. So this is not gonna do any work. This is the only component that is gonna do work. So it's B cosine theta multiplied by delta S. Or UB is equal to the integration from S1 to S2 F cosine theta ds. So F is 400. Cosine theta, the angle between the force and the distance is 30 degrees, because this is 30, so this is gonna be 30, so this is the force, and this is the movement. This and this. So cosine 30 multiplied by the integration from S1 to S2 to ds, so it's S2 minus S1. So this is gonna be 400 cosine 30 multiplied by 2. We're gonna get 692.82 Newton meter. So, as I said, I found out the component in the direction of the displacement. It's B cosine theta multiplied by the delta S, which is 2. It's gonna give you this value or this result. Same thing if you start from first principles, and this is what you are supposed to do in the exam. You integrate F cosine theta ds. F is 400, the theta between the two forces is 30, multiplied by delta S. Does anybody have any questions so far on getting this force? So if you apply the concept of getting the force and the direction of the displacement in all the types of forces, friction, weight, spring force, it's gonna get you to the same result. That's what I did here. I tried to find out what is the component of this force in the direction of the displacement. B cosine theta, multiply B cosine theta by 2, you get this value. Okay, let's find the work done by the spring force. Work by spring. Work by spring is a little bit tricky because, as we said, the US over here of the spring is equal to negative 1 over 2k multiplied by S2 squared, S1 squared. So this is gonna be, but I'm lucky in this problem that the spring is in the same direction of the movement. Okay, so the spring force is in the same direction of the movement. I'm lucky for that one. I'm gonna show you an example that sometimes the spring is not in the same direction of the movement. So I'm dealing with the entire k. So it's a negative 1 over 2. and K is equal to 30 Newton multiplied by S2 squared, 2.5 squared minus 0.5 squared. So this is going to be negative 19 Newton mean. All right, so this is here. Okay, so this is work number 3. Work number 4, friction force. How about friction force? F work, U friction. U friction is going to be equal to the force of the friction, F of friction, multiplied by the distance, delta S, multiplied by cosine theta between them. But usually the friction in the same direction of the movement, so cosine theta is equal to 1. So this is going to be equal to mu friction multiplied by the normal force multiplied by S2 minus S1. But I didn't talk about friction, and I said it's a smooth surface. So if it's a smooth surface, so mu F is going to be 0, and this is going to be 0. Or if I didn't say anything about the friction, you don't have to do this step. But I'm making this step just to show you if there's a friction, what you should do. So you're going to have a mu friction. You're going to say, okay, I don't have any work done by the normal force, but you will have to get it so that you can get the friction. Okay, so I multiply the mu friction, multiplied by the normal force, multiplied by the distance. And definitely, the normal force doesn't exert any work. So the work done by the normal force is 0. So let's get the total work. The total work, U total, is going to be the summation of all the U from position 1 to position 2. Okay, but I need to keep attention to the signs. So some of them are positive. Okay, let me ask you, what are the forces that makes positive work? Positive work means that the force is in the same direction of the displacement. So, or the force is the one that makes all the work, that moves the body. So there is some forces that makes positive work, and there is some forces that you need to overcome them so that you can do the work. So what the forces that do the positive work? The B, the external force, right? And what is the forces that do the negative work? This we need to overcome what? The spring, and need to overcome the weight. So if I want to move this bottle up, so I have to do positive work to overcome the negative work by the weight. But if I lift this bottle from here to go down, so this bottle is making a positive work or a negative work if I lift it.
Oh, you lift it or you put
No, sorry, if I leave it.
If you put it down, it's
Yeah, so it's gonna make a positive work, right? Because the weight is going down and the displacement is going down, but the weight is going down and I'm going up, so I'm putting more work by my hand so that I can overcome the weight, the work done by the weight, which is going down. So that's what we need. And it also takes us to an interesting topic, which is the potential energy. So here, this bottle have a positive, have a potential energy, and when it goes down, it loses some of the potential energy that it has, which is mg multiplied by h. But we are going to talk about energy maybe today, but we will see. I just want to show you if the spring force is not in the same direction of the. If you guys remember the problem that we solved like last week or the week before, do you guys remember we had like a bar? This is very, very interesting problem. Bar like this, and we have a collar here, and the spring was here, and then it came here. Okay. The thing is, this is very, very difficult problem. It's not an easy one. It's easy to solve as a force, but it's difficult to solve as a work. Why? Do you guys know why?
Because the spring is done.
Yeah, and how this makes it very difficult. Like how when however here, like when the spring in this position and this is moving down, the spring doesn't exert any work. But the thing is, the spring is here at this moment, and then here at this moment, and then here at this moment. So the angle is keep changing every moment. So cosine theta between the force and the displacement is keep changing. So I cannot take cosine theta out of the integration because it's keep changing. So I have to keep it. All right. And also the force in the spring is keep changing. Right? Because right now I'm saying that the force of the spring, F spring, is equal K spring S. S is keep changing. Right? Like here has allocation, and I'm only interested in the force in the direction of the movement. Like at this position, this is F spring. F spring, not all the F spring is making the work. The angle between them. So here F. Let's say that this is theta. Okay, you can actually break theta, but if we want to be consistent, theta is the angle between the displacement and the force. So actually this is need to be theta. So this is going to be cosine theta, so it's sine theta. And this is going to be the F here is F cosine theta. So F cosine theta, F spring cosine theta. So F spring is equal to K multiplied by S. And then it has cosine theta. So be careful about that. Try to think about this problem and solve it with work and energy. It's not gonna be an easy problem, and the integration is gonna be hard. I believe I solved it somehow in the notes, maybe in the notes from next lecture, maybe I can solve it next lecture, but it's a very, very important problem. Try to focus, like sometimes, yeah, you are gonna say, we have here the work of the spring, I'm gonna put this right as it is, but this is a special case if the force is in the same direction of the spring. But in this case, the force of the spring is in completely different direction, like it keeps changing as the body is moving. Alright, so right now I'm done talking about work, so let's talk about the principle of work and energy, how we can relate them to each other. Principle work and energy. We need to relate the work with the kinetic energy on a body. So I'm gonna start with, like, if I have a curve and I have a body on this curve, something like this, and I wanna work it as a tangent normal. So let's say the summation of the forces on this body that comes from the weight and everything is something like this. This is the sum of the forces. And solving this problem, you need to find that all the forces in the tangent direction, and I need to find all the forces in the normal direction. And actually, this is also the velocity and the acceleration and everything, but let's find out, if you guys remember, what is the summation of the forces in the tangent direction is equal to. If you guys remember, when we solve the tangent normal, we divide the forces into tangent, normal, and make F tangent is equal to MA tangent, and the normal, summation of the forces in the normal is MA normal. You guys remember what is the value of A normal?
V squared
over rho, right? Okay, so A tangent, if you guys remember the difference between the tangent acceleration and the normal acceleration is the acceleration that needs to make this body moving on a curve. But the tangent is actually similar to the linear acceleration. So is the body is accelerating or decelerating? Okay, so I have a tangent, if you guys remember from the acceleration rule, is equal to v tangent, which I don't have to put tangent because always the velocity in the tangent direction, dv, dt or ds? Do you guys remember? ds. Why? If you want to go always from the first principles, a is dv dt. Okay? You can actually multiply ds up and down, so you can actually make dv and put dt down here, and put ds here and ds here. They can slash each other. And ds dt is actually equal to v. So this is v dv dt. This is how, if you want to remember it every time. This is very, very important rule. If I substitute the acceleration here, I'm gonna have the sum of the forces at tangent is equal to m v dv ds. I can put ds here, so I can have the sum of the forces tangent ds is equal to mv dv. Why did I make this? Because I know that the only force that can exert work on a body is in the same direction of the motion. So it's always the F tangent. F normal doesn't do any work because it's a normal to the motion. So I'm only interested in the summation of the forces in the tangent direction. Okay, so if I integrate both sides, here and here, I have to integrate this one from S1 to S2, and since this is dV, I have to make it from V1 to V2. The integration of this is gonna give you we can actually put it this way, S1, S2, summation of F tangent, ds. This is gonna be, what is the value of this integration? mv, we want to integrate with respect to dv. mv squared over 2, excellent. So I'm gonna have, this is gonna be half mv squared from v1 to v2. So this is gonna be half mv2 squared minus half mv1 squared. This is work. Why? Because it's a force multiplied by displacement. So this is work, the work done by the force, total work. And this one is energy, kinetic energy. Since it has velocity, so it's an energy, and we call this T2, and this is T1. The energy of the kinetic energy at the final position and the kinetic energy at the initial position. And this actually takes us to a very, very interesting rule, that the work from point 1 to point 2 for all the forces on the body, so let's say sum of all the work, is gonna be equal to the kinetic energy at the final position minus the kinetic energy at the initial position, which is half mv2 squared minus half mv1 squared. Very, very important rule. Or actually sometimes we put it this way, that the energy at the final position, T2, is equal to the T1, the energy at the initial position. Like let's say my body, okay, let's say that you are driving a car, okay? A car here, and you put your foot on the brake, and the car is still moving, okay? So here, you put your foot in the brake, and then the car is stopped here. So this is the final position. So this is 1, and this is 2. So the energy at 2 is equal to the energy at 1 plus the work done from 1 to 2. So the energy at 1 plus the sum of all the work done from 1 to 2. Same thing. If you have a water bottle and it started like from this position until it drops on the ground. So the energy at 1 plus the work of all the forces until it gets to the ground is equal to the final energy at 2. Okay? So these are very important rules. Alright, so I'm gonna stop here today, and next time I'm gonna solve an example on the concept of work and energy. But you need to memorize this rule, not next time, I mean next week. Alright? Just one final thing. Try to study hard for the exam because it has a very big chunk of points from your grade. I know that Always Dynamics has a low passing rate. Not 100% of you are gonna pass the class, definitely. That's known in any university. Okay? So I'm not scaring you. There's definitely many people who doesn't attend the class. If you don't attend the class, you lose tracking of things that is in the lecture. You lose many things. Sometimes okay, I'm smart, I can do this on my own, okay, whatever. But study very well. Study the notes very well. Solve as much problems as you can. And try to make sure that you understand the concept. That's everything. You understand the concept. Try to understand the concept of the kinetics, memorize the rules, memorize yourself with the equation in the sheet so that you can use them very well, because we have 25 points next time. Just focus and then solve the exam. Focus on the notes, focus on the homework, and try to solve extra problems to familiarize, because if you get yourself used to problems that you already seen before, no, the exam have problems that you didn't see before, okay? So try to familiarize yourself with new problems, maybe from the textbook, and see if you can solve them or not. If you cannot solve them, there's a problem. If you cannot think how to solve them, there's definitely a problem. Because in the exam, you will definitely see problems that you never seen them. So try to familiarize yourself with problems that you haven't seen before, and then get used to it. As I said, chapter 12, chapter 13, divide your time. You have 1 week. Maybe you study over the weekend. I don't know how you do your time, but it's 25 points. Try to focus to get them all.
Thursday.
Oh yeah, Thursday. Maybe you studied over the weekend. I don't know how you.
If you want to take some time, that's fine. No, but you're gonna have to take some
Doesn't make any difference. All right, good luck, guys. Let me stop the.
No, I'm only going to be